Okay, so maybe we'll start. Are there any questions from the previous lectures about the project? Anything? Okay, then we'll continue with ultralight bosons, and then we'll talk about their detection. Let's say now we would like to write a Lagrangian density for a ultralight boson field. Like, where would you start? Like, what first thing you have to write? How would you start writing the Lagrangian? What? Okay, so, I mean, if the field is varying, there has to be some derivatives in a Lagrangian. And then what other important things have to be if you start putting derivatives together? What's a requirement for the QFT? Lorentz invariance. Okay, and there is like, of course, we also would like to have the lowest dimension operator possible, and that's pretty much it. We can just write the derivatives and see what we get. Okay, so the simplest form, which is Lorentz invariant, okay, you just have this. So for reasons which are not important, but we would like to have things work out correctly, we'll put the 1/2 factor, but this is ad hoc, so. Okay, so d mu squared. Okay, and that's pretty much the simplest Lagrangian you can write. I mean, it tells us so far nothing about the field. So, okay, let's put it in an equation of motion and see what we end up with. And we kind of know what we end up with, but let's just go through the motions. So this is 0. And then your Euler-Lagrange equations would be this, d mu phi. And this is d mu phi here. So, and in this case, and this has to be 0, and we end up with actually very simple stuff. So you have df dt squared is 0, and the solution is obviously the plane waves. So the E, and well, some field amplitude, IET minus KR. Actually with a minus sign. Let me write it better. So I KR minus omega T. Okay, bless you. Is that a good dark matter? Doesn't have mass correctly. So, okay. So let's add the mass term to the Lagrangian. And that's kind of, the simplest procedure you have. And in order to actually have the terms have right dimensions, I mean, it's m squared, phi squared. And let's put 1/2 again. And we have to put it with a minus sign because technically now we have, kinetic energy minus the potential energy. And if the fields get larger, then potential energy has to get larger. That's a minus sign. And one of the reasons why we're doing so, because in this case, okay, your omega square is k square, and therefore the mass is 0. Okay, so we'll add another term, minus 1/2 m square phi squared. And pretty much the only thing which it changes in this case is dispersion, dispersion relations, because now this is no longer 0 in this case. So what we end up with, it's pretty much the simplest bosonic field which you can get in this case. So now minus 1/2 m squared phi squared. And let's rewrite this a bit. Now your first term, your derivative, this is minus s squared phi. And therefore we get d mu plus m squared phi is equal to 0. when we, again, differentiate everything, and that's what we get. And essentially, that's how now we have mass, and we end up with a dispersion relation, which is appropriate to our ultralight bosons, and our solution is actually pretty much very similar, but let's explicitly put the energy in. So minus E, ET minus some PR. And now, in this case, mass is not zero, so the E squared is now P squared plus K squared, plus mass squared. And let's just draw how it looks like. And this is going to be our E. So if there is no mass, that E is equal to just P. And if you do have a mass, it looks something like this. So the E square root of P squared plus M squared. Well, what do we get out of it? What we get out of it, it's this. If your field is cold, if the dark matter is cold, it pretty much means that omega is approximately the mass. Well, up to the appropriate units. So this means, as you see, that your field oscillates at about the Compton frequency. And that's a result which you'll use again and again. And this is true for all of those ultralight fields. You can write more complicated potentials, less complicated potentials, but this is a key thing which we kind of introduced ad hoc when we were discussing those Compton wavelengths and the de Broglie wavelengths last time, but this is pretty much where it comes from. So you write the simplest possible Lagrangian, and you automatically end up with pretty much the cosine wave. And that's what we're dealing with here. Any questions? Well, you can write more complicated potential. So what's the simplest extension to this potential? Well, I mean, you have now this term phi squared. And the most simplest what you can add, you can just say, well, there is some sort of n from, say, 0 to infinity, Cn over n, phi to the n. So you can add the term, which is something lambda squared over 4, phi to the fourth. Okay, y to the fourth, and it's kind of nice to kind of stop there, because at that point your theory is still renormalizable. You can demonstrate this. It's actually demonstrated in the book if you're interested in doing that particular exercise. So this is one other possibility. This is a simplest extension to the field. Why do we care? Because this potential becomes looking interesting if you switch the sign of the square term, quadratic term relative to the quartic term. Because now, the potential actually does not, potential itself has shift symmetry, but the field doesn't. So let's draw how that looks like. So now this potential is not particularly interesting. So if you just have this, the quartic term, mu squared phi squared, plus lambda, and phi to the fourth, that looks like this, right? Well, let's put the minus sign. So if you do this, minus mu squared phi plus lambda then you get this. Yes? You could put a cubic term, definitely. There's no reason, but as I said, we just want to end up with this right now. So yes, absolutely. There's various terms. As I said, you just, again, in many potential you would. In fact, you would in some of important cases, but for now, we would like to eventually end up with a mechanism for the production. So, and this is one of the obvious potentials when you actually get this. Why is that important? Because this actually breaks reflection symmetry. Because now you have two different minimum. So your potential case itself does have reflection symmetry, but your zero field point does not. So in this case, you actually do not get this. And I'm not going to go through the entire case when you have two fields, and especially when you have a complex field. So if you have two field or a complex field, then this actually becomes a Mexican hat potential, which you have seen, of course, in presumably many pictures. So this is the essence of spontaneous symmetry breaking. Now, none of this tells you why this field should be ultralight. But again, we can demonstrate that what you actually need for that also to the field to be ultralight, you also need to actually introduce explicit symmetry breaking, in which your potential itself actually does not have reflection symmetry. And all you do, you just tilt your hat. And that actually would lead to the explicit symmetry breaking in this case. And as I said, there is an entire chapter in the book with detailed explanation. But here we would like only get the essence and also see how, in this case, you can also actually produce those ultralight fields. And in this case, you can actually start demonstrating you naturally end up with ultralight fields. So any questions so far? Well, and now, how do you produce stuff like this? Well, first, there's no reason why you, in principle, can't produce those fields thermally. Because if you, for example, talk about ultralight field, which is an axion, because it has to solve the strong CP problem, has to couple to gluons. And therefore, it automatically can be produced through exactly the same mechanism. So for example, with those gluons, okay, you can actually have, well, diagrams like this, and this is your normal standard model coupling. Now this is not a standard model coupling. That's an axion, and that's another gluon. Okay, that will thermally produce axions. Well, what's the main problem when you're producing thermally ultralight particles? Who can tell me? Yes, so they will be relativistic at CMB. And this means they actually have not a bad limits on a number of degrees of freedom which are relativistic at CMB. And there is some leeway in this case, but I think even in the case if you actually allow to thermally produce axions, and that actually depends on the particular temperature, depends on where the phase transition is, so it's not a trivial thing to say whether you could or could not actually produce a specific type of QCD axions thermally. But even if you do, your limit, you're allowed to do like 2%. So that's, and also this is not good dark matter. So for all purposes, the ultralight dark matter fields are produced non-thermally. They're just too light to be produced thermally because they're relativistic at CMB. And it's a very easy way to do it, to see that's exactly the same reason why neutrinos are relativistic at CMB. And axions are much lighter than neutrinos for the most part. At least the total neutrinos amount to like 0.1 eV. And in this case, we are dealing with everything under the 0.1 eV particles. And when we talk about production mechanism, one thing which you would like eventually to be able to compute something useful. So we would like to demonstrate where you can actually end up with dark matter density. And that's where that becomes complicated, because in principle for ultralight field, you can demonstrate that you can get dark matter density. But the production mechanisms can be either very easy or very complicated. And what doesn't actually, why that matters? Because the way you actually produce those fields, in this case, that at some point you have some sort of a phase transition. And like, when does it occur? Does it occur before inflation or it occurs after the inflation? So those relative temperatures are important. Because what happens if you actually, this field, the values of the field is therefore inflated and then frozen? Well, let's see. So let's say we have some sort of before inflation values of the field. And like here it's bigger, and here it's smaller, and here it's bigger, and here it's smaller. And then inflation happens. What does it do? Okay, well, let's say the value of the field it's theta. Okay, and here is the theta, it's say, like 0.2. And then inflation happens, and that entire region of the universe inherits the value of theta 0.2. This region, let's say, has theta 0.0001, and when it inflates, it inherits that value. And essentially, that's what we're seeing, because that's our part of observable universe, and we just fixed the value of theta here. So in this case, it's actually not possible to predict a region for the axion mass, because now your resulting density would depend on that initial value squared. And we don't know what that is. It's random at this point. And this is actually one of the, yes? Sure. I mean, if you know, if you do the computation for your dark matter density, that actually be proportional to the theta squared value. And because theta squared value is different here and here, now remember that in this case, that will also affect the baryon density. So now the whole thing is kind of observer dependent as well. So this is fairly complicated if you think about it. So there are various theoretical implications of this. But for our purposes, this is a scenario where actually the axion, QCD axion mass is unrestricted. Because you can just plug any values there and you can end up with dark matter density which you want. Well, but in your region of the universe, they're fixed in your observable horizon region. So, but more interesting things actually happen when your inflation happens actually then in a different relation to your phase transition, to your whatever is actually producing those particles. So in this case, now your field actually varies. So now we have a scenario when whatever happened during inflation, we don't care. Somehow the field got restored afterwards, so this is actually our present day scenario. Well, not present day, but the scenario right after the inflation. Present day, of course, it's different. So now this is our version. And what does it do? Well, that actually has different values of the field. So what it does, it forms domains, and it forms strings. And then both of those things eventually decay. So, dark matter production has to account for all of this. So there is a very beautiful talk actually given just on the subject here at JGI. I'm going to actually provide the lecture to the link to the lecture, which is just on the productions of axions, because otherwise we'll be here for a very long time. Okay. Now, this is a secondary production mechanism. So if this scenario happens, then you can actually have to account for domain wall strings. They decay, some of it's relativistic, some of it's not. But the main production mechanism, it's still, in both cases, it's vacuum misalignment. In the first case, that's the only mechanism. In the second case, you also have to deal with the fact that you actually have some weird topological structure here. And when they decay, they also produce axions as well. Okay, and then to the misalignment mechanism. This is really exactly what it sounds. So the whole idea of the vacuum misalignment mechanism is that your field value, which you eventually end up with, it's different from the one where you started. So the main idea that the initial value of the field is different from the minimum the field end up with when everything is said is done. And all it is, it's honestly just damped harmonic oscillator. And let's see how that actually works. And that's actually why I call the misalignment mechanism, because the original field is misaligned with its final value, which we actually get now. Any questions so far? There's been questions about production, so that's I thought I'll include all of this. Okay, now, when we're solving all of our equations, we always assume so far the flat matrix. Now, in this case, we are not allowed to actually use flat metrics because we actually are in a region where the universe is still significantly expanding. So, well, let's use this Friedman-Robertson-Walker matrix, FRW, and this is just simply this. So these are moving coordinates. This is some scaling factor, so the R is a scaling factor, and then you have dx, dx. So all we have to do, we have to solve equation of motion for the field with this matrix and see what do we actually get. Okay? So if actually we write it down, we have this. And again, the scalar factor, again, it's all time dependent as well. And this is just because when you actually do differentiate, now you have this term, and this is time dependent, so your derivative, when you actually do the derivative, you end up with extra terms here. That's all it is. And then now you have a gradient of the field squared. And all of this, you end up with a field Tx. And okay, and if we write all of this, and if you write with a potential, if you add potential to this term, we can actually track down that all you have, it's simply this. So now this is a Hubble parameter. This is the first derivative of the field. And I didn't explicitly write the potential in this case, but I will do it here. So in this case, you end up with a damped harmonic oscillator. And the things which go into the phi squared, I switched units a little bit, plus your mass squared. And in this case, all you do, you can assume that your potential is, well, d phi is equal to 0. And your potential, let's assume the simplest case, again, m squared phi squared, but you can actually make more complicated ones. And what happens with this field? What happens with this field, essentially, initially, is what's called a Hubble friction. So the field is stuck. So if your parameters, in this case, have the case then a 3h is larger than omega, then the field is constant. So the reason why that happens is that the harmonic oscillator was called overdamped. So your one wave function wavelength does not fit into the horizon, and the field is not allowed to oscillate in this case. And if you actually draw the potential, or if you actually draw the energy of that thing, so if you draw the energy, okay, so you have something like this, and initially the field, your value of the field is just stuck here. And this in the case, for example, if we have an axion, then it gets stuck here until the QCD confinement, until about 200 MeV. Because this is when, in this case, this condition would actually apply for the QCD axion. And then, when this condition no longer applies, you suddenly get a case that wavelength actually fits inside your horizon. And now oscillations are no longer damp, and the field allowed to oscillate. So all it is, it's actually just comparison of your the Hubble parameter to the potential which you get. And because both in this case are time dependent, when then the field is released, essentially what it does, it starts rolling down. And when it starts rolling down, it starts oscillating. And remember, in a quantum field theory, what is the quantum of the field? It's particles. So that ultimately, therefore, are produced. So the field starts oscillating. That's producing your entire, essentially, dark matter. And eventually, of course, the oscillations go down, and the field gets stuck in whatever its minimum is going to be now and forever. And that's a basic idea for the vacuum misalignment mechanism. Now, there are a little bit different variations, whether the thing is scalar, pseudoscalar, relaxion, or which is kind of pseudoscalar, or vector. And in the books, there is, all those differences are pointed out. But this is just a simple idea. We are just dealing with a damped harmonic oscillator, and it's not allowed to oscillate until the specific conditions are satisfied. Now, in the context of axion, that's actually what solves the strong CP problem, because your initial value of the field of this, which corresponds therefore to the theta constant which you discussed. So remember, with a problem with a strong CP, that you actually have this term in the strong interactions, which is allowed, and this somehow has to be very, very small, less than 10 to the minus 10. And we don't understand how it happens. Well, the way it happens now, that this is a dynamic field. And when you actually reach the QCD confinement scale, then you end up with a case that the field starts rolling and starts oscillating, it's producing axions, and then it gets stuck at the point theta being 0. And that's why we have theta being 0 now. There is a different versions of that. Let's say it didn't quite actually get stuck in a theta 0, and the CP violation, you leave a little bit of a CP violation. Then you end up with not QCD axion, but with ALP, which is like axion-like particle. So in string theory, you can end up with a variety of different pseudoscalar or scalar or actually vector particles. And therefore, it's important not just look for the QCD axion, which actually will solve strong CP problem, but the whole plethora of various particles. And we actually look what kind of coupling to the standard models they actually have. Questions? Yes?
Sorry, I didn't get why not exactly 0?
Oh, why it's not exactly, it just, as I said, to solve the strong CP problem, it has to be exactly 0. Well, it's not exactly 0, like we end up with 10 to the minus 10, but it's likely this is just 0. And we're just, as of measurement right now, we are seeing that we are restricted by the neutron EDM. In fact, there is a very nice cartoon which kind of tells you, okay, don't take it very seriously, but you have 3 different quarks, 2 the same, 2 different, and think about the angle, it's kind of the angle between the quarks. If they all align, so you have 2 of them the same charge and 1 other charge, then there is no dipole moment. If they misalign, that you have a dipole moment. This is a classical, absolutely classical picture of neutron. If you just take it to the absolute value, take a radius of the neutron, take what the dipole moment should be, you get that you have about 10 to the minus 13 theta, 10 to the minus 13 theta or so on. Actual calculation 10 to the minus 16, and it's an ECM units. And now your actual value of the dipole moment, so is right now restricted by about 10 to the minus 26. This is why that has to be less than 10 to the minus 10. But you can kind of just end up with a just silly picture of the 3 quarks in the neutron, define the angle as a kind of misalignment angle between actual physical, classical kind of like particle, and you end up with a minus 10 to minus 13 if you plug the radius of the neutron and the charge and what dipole moment you can get. So I've only seen it in a single talk, just because it's kind of such a weird classical picture. So by the way, in terms of this EDM, effects. I will talk about it more. But when you say, okay, 10 to the minus 26, it doesn't seem to be, okay, it's impressive, but it doesn't mean anything. So let's put some, again, ideas of classical case. For the case of electron, what essentially it means for electron to have, or for neutron to have an EDM, that your elementary particle is kind of not spherical classically. It's kind of squashed. So how much effect of the squashiness do you think you can get? Well, if you blow up your electron to the size of the solar system, your squashiness is the width of a human hair, 10 to the minus 30. So those experiments are fantastic. So again, the solar system, width of a human hair, that's how they squashed on the poles. So it's like a very, very, very small thing. So those are extremely precise experiments. And it's going to be interesting if they actually do see the neutron EDM, because it could be theta term, it could be standard model, which would be just standard model, or it actually could be not standard model. And I talk to people, it's not going to be easy to actually decouple this. Because the predictions of the standard model, I mean, you can make them, in principle, what the EDM of neutron would be from just basic standard model from the rest of everything else except the theta term, write all the loop diagrams and so on. But this is pretty model dependent. So in this case, if you measure both EDM of neutron and a proton, that you can actually do some separation, but even that is model dependent. For the EDM of the electron, that's very straightforward. You see EDM of the electron, it's not standard model. Because EDM of the electron standard model is 10 to the minus like 43. You need 3 loops to generate EDM for the electron in a standard model. So it's extremely suppressed. So this is one of the most specific science of BSM physics if you actually see electron EDM. And I will talk about those molecular measurements. But the EDMs are pursued with neutrons, with protons. People have, there are in those documents which I showed you yesterday, there is idea how to measure EDM of proton storage ring. It's very hard to measure EDMs of the charged particles. In the case of electron, it's easy in a way because you get it bound into molecules on an atom, which the whole thing is actually neutral. For the proton, you can't do it, you have to do a storage ring. For the neutron, it's more straightforward. But then extracting the EDMs of the hadrons from the EDMs of atoms is very, very hard. Okay, so to summarize, we can write realistic ultralight dark matter. So we understand that it oscillates at Compton frequency, and there is a misalignment mechanism which can produce it. And there are other production mechanisms, especially for axions, when you end up with domain walls, that you have domains, you have walls, you have strings, they all decay, and there are multiple production mechanisms in this case. So actually computing the density is complicated in both cases as a result. Now, however, people were able to actually do some computations, and in the second case, when you actually post-inflation, you can make some sort of prediction on preferred mass of axion. And that's where people have been concentrating so far. And that's why most of those experiments do concentrate in the 10 to the minus 3 to the minus 6 range, because that was initial prediction. It does keep shifting a little bit to the higher masses, but it's, when this idea came out, it was understood that technically QCD axions can be absolutely any mass whatsoever, because you don't know what original theta value is and you don't know what the mass is. You do know that the mass and decay constants are connected, and that is prediction is valid in both cases, but then you don't have any idea where the mass should be. So now actually the idea is to search for QCD axion through the entire range all the way down to 10 to the minus 22 and all the way up to the limits from astrophysics. So, and one of the interesting consequences of the axions, and I'll show you why, that you convert actually axions to photons. And that really does bad things to solar physics. It also significantly affects supernova explosions. And that's why you actually constrain to the axion mass from the above, because then you get data from the neutrino emission from supernova in 1987. And the axions will affect the duration of the neutrino pulse. And that actually completely corresponds to the standard model predictions. So that's why technically axion has to be ultralight. So the heavy axions were ruled out by the beam dump experiments a long time ago. So in this case, a mass has to be like less than 10 to the minus 2 electron volts. So it's an entirety now in the realm of kind of those quantum type of experiments. So any questions on this so far? So I decided I'll go over this because there have been questions on production. And this is one of the main mechanisms for those cases. It's non-thermal. And the other thing, it's completely disconnected from the detection mechanism. So if you do actually see an axion, proving that it's 100% dark matter would require also seeing solar axions as well. because then you can actually have different data points. You can decouple, then presumably you can try to decouple the density in this case. But this is actually not going to be easy. So for anything except the most straightforward WIMPs, proving that your particle is 100% dark matter is very difficult. But even for WIMPs, you can avoid direct connection between production and detection as well.
I'm sorry, can you repeat, even with WIMPs?
Well, because with WIMPs, you can always make the case when you can make some particle and then it decays to your WIMP. And then you disconnect production from detection. So that's the easiest way of avoiding it. But if you have straightforward, that's the same mechanism for the production detection, then technically you can actually run some numbers and see whether you can actually get the full density. So. But of course, there's also possibility that WIMP is not the only dark matter particle. And the one question which been asked yesterday, and I thought I will cover it in some more detail, is, sorry. Disconnect this. So why are we actually, besides the action, what is the motivation for the ultralight particles? And action is one of them. And actually I looked up yesterday, and apparently you can actually use actions to solve all three problems. So there's been a recent paper in PRL in 2020 which called axiogenesis, which actually showing how with actions you can actually also solve the matter-antimatter asymmetry problem. So I don't know whether there are significant loopholes in that or not. I actually didn't have a chance to read the paper, but there have been already papers that with actions you can solve everything. So you can solve you can actually solve the strong CP problem, the dark matter problem, and with actions you can actually solve the matter-antimatter asymmetry problem. With relaxion, you can actually also solve the hierarchy problem. So in this scenario, all your new physics will ultralight, period. There is nothing at TV scale. And this is an interesting scenario. So again, how probable that is a good question. But at least there are theory papers which actually can make all the problems go away with no TV scale physics to be seen. Okay, so therefore, let's summarize, what is our motivation for the ultralight dark matter? Okay, the first axiom solves strong CP problem, possibly matter-antimatter asymmetry. And now, strong CP problem actually is very, very hard to solve any other way. There is really no good solution for it besides the QCD axiom. And also, there is no really anthropic reasoning why that actually should be, why it should not be CP violation in strong physics. Because you see, it's kind of bizarre. From one point of view, we're missing CP violation in standard model. And in the other case, for some reason, we could have a CP violation with this term, but we do not. So those are two separate problems. And it's kind of slightly bizarre that they're kind of counterindicative. So matter-antimatter asymmetry. And in principle, then you're also solving the dark matter. And it had been demonstrated that that can be 100% dark matter. There's no question that axion can be the only dark matter particle. So now you also can have extension to things called ALPS. So in axion, there is a very specific connection between the decay constant and the mass. In ALPS, you're decoupling those things because you get that from solving the strong CP problem. If you're not exactly solving strong CP problem, you have a little bit of a CP violation term remaining. Then you actually have the whole other slew of particles. The reason why that is motivated because you end up with those particles if you start doing anything involving extra dimensions. Those will naturally produce ALPS, axions, scalars, and actually even vectors. And that's another motivation for it. So for the second one, by the way, can you hear me well in the back? That seems to sometimes, okay, all good. Turns off, relaxion. And that's a hierarchy problem. And with third one, it's all of the GR versus QFT. So trying to do any connection between the general relativity connection to quantum field theory automatically ends up extra dimension, which pretty much automatically provides you ultralight particles. So, and this is relatively unavoidable. This is why there is a kind of somewhat prevailing opinion that there could be the whole dark sector out there. And there could be way more particles than just one. So as you see, the ultralight fields are actually just as well motivated as having heavy dark matter, because you can solve all of the same problems, plus the strong CP problem, which we really don't know how to solve any other way. And now the important part, how does any of this actually couples to standard model? And in this case, you can simply just write all possible low-dimensional coupling and then try to think about what will they do to all of your devices. So and that's how we'll pursue this. Any questions on anything so far? Yes? What? Oh, Fa is a decay constant, and Ma is axion mass. Okay, that's all it is. So essentially, that's your scale. Yes? What? No, QCD axions have definitely not been ruled out, so. Oh, the heavy, yes, because so what they did, they for a while thought the axion can be fairly heavy. So what they did, you just put accelerator beam onto the wall, and that will produce axions if it's heavy.
So the people who did the axion kinesis paper with regulatory thing, they're saying that in the axion kinesis scenario, you can actually get back some heavy QCD axion.
I have admit, I found it yesterday night, I have not read it.
Okay.
So I just, because yesterday we were talking about whether you can actually solve it, so I was actually looking at the references, and I found the link to that paper, so by Raymond Coe. And if you're interested, I'll provide you the link, but you can just Google axiogenesis and you'll get the parallel paper. So I think there's only one other on that. Okay, that's an interesting point. And there, I think the main idea, you also make the axion field rotate as well. So, and that's what does it. Okay, so let's then talk a little bit more about the limits, and I will show you the limits for axions later. But somewhat surprisingly, one of the absolutely best limits on quite a lot of those things, especially the axions, is that in 1987, a supernova exploded in the Magellanic Cloud. Now, that is like the closest supernova at the point that humanity had neutrino detectors. And Super K had seen like, what, 17 neutrino, 17? So you can say, like, what can you get out of 17 neutrinos? Because clearly the flux is very large. Apparently, it's not the number of neutrinos, it's the duration of the flux. So apparently, the duration is fairly significantly constrained, because what the axions do, the axions actually have this process. When you have two photons in an axion, and this process can go either way. One of those photons can be virtual. And this will actually significantly affect the supernova's explosions if the axion is fairly strongly interacting. It also will significantly affect the life of stars, which are heavy. It could even, affect stars like our sun. And all of those limits are put together. But surprisingly, the supernova limit is actually one of the best ones. And that actually constrains, that's one of the ones which is used to constrain the axions. Now, if those things are ALPs, and I think the ALPs can actually also, in this case, actually solve the, so you don't really need a QCD action, I think, for this. You can actually do the ALP. The problem now with the ALPs is that ALP parameter space is much less constrained because there is no connection between the decay constant and the mass. And you can actually do the axiogenesis with ALP. And in this case, your coupling to the standard model are not as constrained as well. So as you see, this is new. This was like 2020. So very, very recent. Okay, and now we get to the realm that we would like to detect all of those particles. And in this case, what I want to do is try to kind of be exhaustive and write out all possible couplings. So let me erase everything. I'm not sure if you need this part of the board, but let's try. And can you imagine how many people are waiting for another supernova to explode? There's like 15 detectors which can see it now, which are going to be online within 10 years. It's like literally, if one of them is not, because in this point, we will get so much new physics if we see a supernova explode in our galaxy. And the point is that the rate is like 1 to 3 per 100 years. So 1987, we're kind of due for one. But again, that's for statistics. There could be nothing for next 200 years afterwards. So, but I've heard a lot of talks about it, actually. People are prepared. Okay. So one of the basic ideas, how we actually coupling the standard model to the dark sector. We are going to stop assuming anything. We are going to say that somewhere we have our standard model, and we also have your dark sector. And somehow they are coupled. So as you see, there doesn't have to be exactly a direct coupling in this case. We just have to say what's called portals. And there are a very limited number of ways you can do it. You can do it through Higgs, through the dilatonic coupling, through the kinetic coupling, the mixing to photons, or through the various charge currents. And in this case, the number of couplings which you can write is fairly limited. And again, the important question is, how do you look for something you don't know what it is? Let's say the database is spin statistics. So you have either spin 0 or spin 1. Well, you can ask why not 2 or 3? Well, the issue with spin 2 is that people actually have problem with naturalness of spin 2 actually particle which has mass. So there are problems with QFT of writing down the natural theory and appropriate, there's quite a lot of different problems there. So the problem is not only with naturalness, and so far they actually have not been solved. So you also problem have with just allowable interactions for the spin 2 massive particle. For the spin 3, there is just no effective theory, no good effective theory for anything which has spin 3 or higher, because none of those theories are valid above the mass of the boson. So that's why we're kind of at spin 0 or 1. On the other hand, there's plenty of things to do with spin 0 or 1. So now we know that spin 0 or 1, and the other thing we need to know what is parity. So the parity is actually R going to minus R. So the parity, it's the transformation under this reflection. So you have essentially a mirror image upside down. And in this case, you can have true scalar or a pseudo scalar, or you can have vector or axial vector. So now, right now, we have 4 choices. And we have to ask in each case how you can couple the sectors. So what's the easiest thing to couple with? Well, it's the easiest thing to couple. It's a scalar with a scalar. You just couple through Higgs. It's called a Higgs portal. Let's start writing down the table. Okay, so I'm going to put spin 0, and type or parity, scalar, and the operator. And here's a caveat. We are only writing the lowest possible dimension operator, because that's technically the ones which should dominate the couplings. There are many other ones you can write. Okay, what's the simplest one? Well, you just have your scalar, and phi is your scalar field, your dark matter field. So let me actually make sure we write down which fields are dark matter. And let me actually say dark matter so it's obvious what that is. So the phi, it's a scalar. And Higgs is here. Okay. And this actually is a relaxation can couple like this, for example. So the scalars which couple through Higgs, you can actually do fairly interesting things with them. So, and this is called Higgs portal. And here I will write consequences of this. So before I write consequences, let me write one more scalar coupling, and that's what's called a dilatonic coupling. It's either phi standard model or phi squared standard model. So this is OSM, that's your entire Lagrangian. So any standard model particle can couple to the scalar by just simply multiplying the scalar, or the quadratic coupling would have a quadratic square of the scalar multiplied by the entire standard model Lagrangian. So that's what's called a dilatonic coupling. Okay, and so we will show what those two things will do to your standard model particle. They will modulate values of fundamental constants. And we will actually demonstrate exactly how that works for this particular case. We'll write down all the formulas for it. So what do you think exactly happens to your quantum sensors when you're actually modulating value of fundamental constants? So what does it mean? It means that you just couple an oscillating term to every term in your Lagrangian. So that leads that all the masses, the mass of electron, mass of quarks, mass of muons, everything, will start oscillating at the Compton frequency of the field. It's a very weird concept, but this is the consequences of doing so. So now, what happens to atoms? Because not only the masses oscillate, the electron mass oscillates, the proton mass oscillates, most important, their ratio oscillate. But most importantly, coupling to electromagnetism oscillate, the fine structure constant oscillates. So what does it do to the energy level of an atom, to hydrogen? Well, it's proportional to alpha squared. So the energy levels become also oscillating. So how would you look for it? The important point here is that not all energy levels depend from alpha the same way. So the heavier the system, the closer your electrons sit to the nuclei, especially if you start removing electrons and getting highly charged ions. And that is essentially a relativistic effect. So there is a relativistic alpha square enhancement. There is also various correlation correction enhancements. And this is a purely atomic computation. I can compute it to fairly significant precision. So in order to compute the effect of variation of fundamental constants on atoms, variation of alpha, all you go into your code, you find that somewhere inside the code has to know what alpha is. It literally has this 1 divided by 137 somewhere. And you just change alpha, you compute a new value of energy, and you calculate the derivative, and that gives you sensitivity. This is surprisingly insensitive to any details of computation. Generally, those are known to like better than 1% to a few percent. So the effect on atoms is no. So because all of the energy levels will be oscillating, what you do, you would like to find one clock, so one device which precisely measures your energy levels, and then compare it to another one where the effect is much larger. So you find one which is a reference, or you find the one which actually is a heavy system and the effect is larger, and you measure the ratios of frequencies. And this ratio of frequencies should actually have oscillating components, and you can do Fourier transform to extract it. I will actually go over that in some detail when we discuss how clocks work. But this is a basic idea. If fundamental constants vary, then any device which measures energy levels technically can detect it. This is a direct detection experiment. You really do the Fourier transform into the frequency domain. You see peak at the Compton frequency of your dark matter. This is a direct detection experiment. So, and we'll go over to actually prove why such couplings would actually cause variation of fundamental constant. We'll write down Lagrangian and see how that works. So any questions on those so far? Yes?
Can you repeat exactly what frequency the peak would be? So what physical significance the peak of this Fourier transform?
Okay. So you have now the scalar, which is oscillating at this frequency. So you measure the ratio of two frequencies which are both oscillating. So you have a series of time measurement. You convert it to frequency domain. You should actually see the asymmetric peak. It's asymmetric because of distribution at the Compton frequency of the dark matter. Okay, that's on top of your laser noise and everything, but it's distinguishable peak. Also, it's actually verifiable peak because we know exactly how that ratio scales for all of the different clocks. We know the sensitivities. So for example, we know that like 2 terbium transition will scale as to 1 to 6. And the aluminum mercury will scale as 1 to 3. So the one of the effects should be exactly twice the amplitude of the other one. So this is potentially verifiable signal. Okay, and this. So nu 1 over nu 2, which is two frequencies, are no longer constants. The frequency ratio oscillates. The frequency ratio of. Oh, in the presence of the field. No, in the absence of the field, it doesn't. Yes, in a standard model, it does not change.
It doesn't change.
It doesn't change. There's no way of. Okay, there are different systematic standard model effects which people account for. And because these are metrology devices, they know all the systematic effects which standard model can cause. And those have been verified at the level of 10 to the minus 18.
I'm asking because one could say, let's check it's constant, and maybe then if I see it's not constant, I do the Fourier analysis. Maybe it's not working.
No, you pretty much have to, in this case, there are certain conditions under which has to be, okay, certain conditions have to be fulfilled for the Fourier analysis to work in terms of how many dark matter oscillations you actually fit into your measurement. So in principle, if you actually see any variances, that's something either wrong with your clock or there is some other effect. For example, Lorentz violation will also change the ratio. But the modulation for Lorentz violation is different. So there are different other effects which can actually make this vary. So the fact that the Fourier transform will actually produce a peak makes it distinguishable as dark matter.
Post-discovery, quote unquote, thinking.
Right. So, but as I said, under certain conditions, you can do Fourier transfer. You just fit in terms of sinusoidal and see if there's some variation. So, but as I said, the post-discovery, you can actually do various other experiments to verify. So. And again, Fourier transform would produce you some of the other peaks. For example, there is a various laser noise, or there is various electric things which actually change, produce like a Hertz level response as well. But those things go away, so you can demonstrate that this one does not. So there are a lot of different standard model things you have to subtract out. So the idea is very simple. Its implementation is not quite. But several experiments already been done. This idea is very recent. The first paper was 2015. So it's extremely recent. I'm going to stop there and give you a 10-minute break. So if you have questions, please come and we can chat. And then we'll continue with all the other different couplings. Any questions so far? Okay, we'll get to the next coupling. Oh, go ahead. Maybe if you put it on the door and you have to assign. Okay. Okay, now there is only one other scalar coupling which you can write. And people actually have not been using that so far. So, and this is, you can in principle couple it to fermion. So this, demi fu, and I'm sorry. And this, gamma mu psi. So this is current. And for this one, I'm not unfamiliar with searches. So you see this part, and you have this part. So as you see, what we are doing here, we're formulating all possible Lorentz conserving terms. So in principle, yes, you can have so this is just current for the scalar field, derivative of scalar field, and then you're coupling your fermionic field. So, and this is mu. And just in case it's listed, and actually this is from the book. I thought I'll use something which you can look up afterwards. And again, let's start writing, just ensure we understand which one of those fields is standard model and which one is not. So here we coupled it to Higgs, and here we're just coupling it to some sort of fermion. So, but I'm not quite aware of the searches. So this modulation of fundamental constants, you can search it with clocks, interferometers, cavities, and other things. I think the current you can actually search with magnetometers. So this is it for the scalars. This really, I mean, if you look, it's not obvious what else can you write, because there is a very limited way. There is no other, with the scalars, there's really no other construct which you can write besides this. At least I'm not aware, yes? Right. But that's for the current. That's the only one you can actually write. There's other things that you can write. So.
And the first one is dimension 3, correct? Why isn't there a pi squared, for example,
That's a good question, because this one actually you could allow to have phi squared. So it's possible, but the problem with phi squared, those are very strongly suppressed. So as I said, this is not exhaustive list. So, and this is mostly what people have been looking for. So you can make high dimension versions of those, of course. Okay, now pseudoscalar. I mean, this is still 0. Okay, simple thing. And now we actually are going to label our field A for the axion, couple it to gluons. So the axions, you actually allow the gluonic coupling. So axion gluon. Right, because you get 3 halves, 3 half, 1 and 1. So that's why you get dimension 5. Okay, in axion gluon couplings, you can actually, okay. Questions? Yes?
Doesn't the scalar field have last dimension 1?
What?
The scalar field has last dimension 1, so it's 3 halves, 1 from the derivative, and 1 from the scalar field. Dimension 6.
Yes, because the derivative gives you dimension, right? Okay. So, well, I mean, that's the lowest one you can write. That's actually why people mostly omit that one. Because people kind of want to start with kind of dimension 4 and down. Okay, so what will this do? So if you actually couple this to gluons, and this is actually very interesting. What it does, it will actually make nuclear EDM, which is oscillating. And surprisingly, it's actually easier to look for oscillating EDM than for the permanent one. So even though that's a very small effect, people actually been looking for it. So this is oscillating nuclear EDM effect. EDM. And the experiment which has been looking for, it's called Casper. Electric. So there is 3 different versions of Casper, and this is the electric version. And I will show the scheme for this experiment. So you see, this is not standard one. This is not the one to photons. That's the one to gluons. And the next one, it's the kind of most favored one. It's when you're coupling pseudoscalar to photons. And this is the F menu one. Okay. So the axion photon. And now this is very popular, so people have been looking for it with microwave cavities and names of experiments ADMX, Carl Tusk, and Haystack. Haystack, I'm not sure how they spell it exactly, and also Mad Max. There is a lot of interesting names. There is like experiments. They literally was able to spell abracadabra. So the action search has been inventive lately in terms of inventing names. And there are others. I'm kind of running out of space here. So, but this is a microwave cavity. It's literally exactly what it sounds. So you actually listen to the action. So remember, at 10 to the minus 6 mass, what was the characteristic length? 130 centimeters. So that's what you do. You actually literally take a microwave cavity, and you think that eventually the action will get there and actions get converted to photons. So which means that you actually will have electromagnetic modes in your cavity, which is produced because of the action. And you literally, it's literally a radio. So only extremely good one. And I will show you the scheme. I'll also, this is one of the most promising way to do it, but the success so far has been limited. There's been very, very little of the action QCD action parameter space rolled out so far. And I think we finally got there, and maybe in 10 years we would actually roll out a very large fraction of it. So, because there are finally completely new ideas how you can actually search for the actions using different types of materials. Okay, so action actually has another coupling. So there is also, so essentially what this causes, and I didn't write down, it causes electromagnetic field along B, along magnetic field. And the way this works, that what this coupling is, remember there's action and 2 photons. So you can actually have one actual photon, and then you can have one photon which is just magnetic field. And that actually here is an action. So gamma, gamma action. And this actually can go either direction. And this is why the actions are constrained by solar processes. Because imagine when you have the middle of the sun, and your nice photons, when there's a pretty strong magnetic field in the sun, so you have photons and magnetic fields, you start producing actions. What happens when you produce actions? It doesn't interact with anything, it leaves. So the actions leave, if the action is produced in the middle of the sun, it gets here in 8 minutes. Do you know how long it takes photon to get out from the center of the sun? Could be millions of years. Because the photon scatters and scatters and scatters, the action does not. So this is a very efficient way of actually getting energy out of the star. So this is why this process actually fairly constrained by the solar physics. Not the solar physics, but the various, astrophysical observations of stars, and as well it will actually affect the supernova explosions as well. And this is called the Primakov process. That's one of the, for a while, people only essentially used this. So within the last few years, there have been experiments actually with oscillating neutron EDM, which is discussed per electric. And there have been also one other coupling. There is also pseudoscalar coupling to fermions. And by the way, the QCD action doesn't technically have to couple to fermions. It could, it has to couple to gluons, but it doesn't have to couple to electrons. But you could make it couple to electrons. And here, it's a derivative coupling, DMA. And then there is a gamma mu. And it has to be a gamma 5 current, gamma 5 matrix because it's a pseudoscalar. So this is action fermion. So, and what this actually causes, that causes spin torque. I'm kind of run out of space there. So this will cause a spin torque. So essentially it causes spins to precess. And that's what people have been looking for. An experiment is called Casper wind. And also there is a GNOME. And actually quarks. As I said, people have been inventive. And this is not the full list. There's many more different action experiments, but there is really only those 3 different couplings which are being pursued because that's the 3 of the lowest dimensional operator which you can do the fermions, gluons, and photons. So you can see why people have been looking for actions for the same reason people have been looking for WIMPs. First, it has to couple the standard model. QCD action has to couple the standard model, just because otherwise it wouldn't be a QCD action. And second, exactly the same couplings which make it QCD action makes it detectable. It's just harder to do than WIMPs, just because, well, I mean, it's a very light particle, and there are very specific type of scenarios which you can actually, very specific type of experiments which you can do to get for it. Okay, the important part, the one other important part which we haven't discussed. The WIMP detectors have to be underground. Does anyone know why the WIMP detectors have to be underground? Like seriously underground, like a couple of miles. Does anyone know why? Yes, from cosmic rays. Now, there is no background for cosmic rays to anything ultralight because there is no scattering. So all those experiments can perfectly be anywhere on the surface. So none of those experiments have to be underground. And at one point, we actually decided to compute whether muons will make a difference because there's significant muonic flux. And there was a concern whether there's any effect of atomic clocks. And then if you compute, you find that several, the buildings usually, of course, have floors of concrete. And it turns out that most of AMO labs, they're always in the basement for various reasons, vibration isolation, so on. So we're just, people like to have offices with windows, so the labs are usually in the basements. So the 5 levels of concrete kills most of the muonic flux. But they actually do not at all affect clocks. We actually run that. So the only thing that muon can probably, in principle, get an ion out of a trap, but it's extremely unlikely. They just move too fast. There is no interference with any of the quantum devices. So that's been actually looked for. So there is no any cosmic backgrounds for any of this. So any questions on the pseudoscalars? So this is the couplings people have been looking at. I will show you, so next time I'll use slides, I will show you how experiments actually look like.
There are coupling ranges that are associated to each of these operators, or the searches of coupling?
We have no idea. So the only thing for QCD action, the decay constant and the mass is connected, and that's it. But you can have any one of those couplings. Yeah, there is, I mean, as for everything, there is no constraint. Okay, and also we generally don't want decay constant to be subplunking, but it's not prohibited in principle. So. Yeah, we don't want couplings to be subplunking, but on the other hand, you could actually probe subplunking couplings with clocks. Okay, so what's next? I think we're kind of out of the space. Ooh, okay. So vectors. What's the most famous dark matter vector? Well, dark photon, sometimes it's called a hidden photon. There is some difference, but we right now don't care. So now we're back to vectors. So spin 1 vector. And here, for the vector, we actually are going to define, you need to define 2 quantities. And we are going to call the vector potential x, and we are going to have this funny f for the tensor. Okay, so the coupling is this, the vector part, and the fermionic part. So this is absolutely minimum coupling, how you can actually couple the vector to a fermion. In this case, we just call it minimally coupled. And what you end up with actually is then the next one. So you have electromagnetic tensor, and then you have your dark matter one, or you can actually have coupling through the vector potential. And this is actually called hidden photon couplings. And this is also sometimes called kinetic mixing. So this is actually some of the most kind of known cases, because now, in this case, what you do, you actually have a photon from this case, but then you have a hidden photon on that case. So you see the standard, in this case, the standard model and dark matter actually do not talk to each other at all. What actually happens, that your photon has a very small admixture of the hidden photon. So, and this is what's kinetic mixing it. There's a consequences of this. With this, you actually end up with a charged fermions. Because now the dark photon will couple to dark fermions, and those dark fermions acquire charge. And this is actually have not been ruled out. And the interesting question of why such a weird thing have not been ruled out, because charged particles are allowed to be very heavy, so they could be TeV scale. I think I mentioned briefly, but we can actually mention it now. Let's say the charged particle, and it's like not like true charge. So it's not just for some whatever reason there is some normal particle which carries a charge. This is literally the dark fermion which carries charge because there is a kinetic photon coupling to it. So let's say that thing hits Earth, it hits an atmosphere, it's fairly strongly interacting. So it almost interacts through almost like effective Coulomb interaction, because it doesn't interact electromagnetically, but in normal photons there is a small admixture of this dark photon, and that what couples to the charged particle. So it's strongly interacting to the point that when it hits atmosphere, by the time it gets to Earth's surface, it thermalizes. So it's literally 300 Kelvin. And eventually it propagates down to Earth, and it hits your xenon 1-ton dark matter detector, and it does absolutely nothing. The reason why it does absolutely nothing to the detector is that the reason why there is so large energy deposition, it's because there is a fairly significant energy of those imparting particles. So you need to actually impart significant energy to the detector, at least like keV, in order to see the signal in any of those detectors. And this is like EV type. It's 300 Kelvin, it's very slow, it's EV. It's not constrained by WOM detectors. It can actually be constrained by trapped ions, because with trapped ions, it actually will hit ion traps. The only reason why that would work, because with this effect, you actually end up in overdensities of charged particles on Earth's surface. That's been realized only like last year, that you can have like 10 to the 15 orders more charged particles on the Earth's surface than the normal halo, just because it gets stuck before it propagates down. So with a charge, you can't, I think, you're not allowed for various reasons to have 100% dark matter, but you could have a significant fraction. And the reason why charge resurfaces is explanation of this Idris experiment of how to cool down the hydrogen in the early universe.
Why do we need a dark or hidden photon? If it has charge, it should be able to...
No, dark photon does not carry charge. So the dark photon results in essentially the fermion will carry the charge. The dark fermion will carry the charge. Dark photon actually could be fairly good mediator. It could be fairly heavy. So dark photon is a fairly, so there is a different scenarios with dark photons. There is a cases when dark photon is a mediator and when dark photon is itself dark matter. The case when dark photon actually is dark matter. That's a different scenario. It can be ultralight in this case.
But since dark matter here has charge, should it be able to interact with photon itself?
Okay, let me just make it very clear. The millicharge is not millicharge particle is not ultralight by itself. It could be a heavy fermion, but it's connected through the dark photon. That's why I mentioned that. So technically, this is different from this, but just because it is enabled by the fact that dark photons can exist with the kinetic mixing. So it's essentially generated through the kinetic mixing, and then you assume that your hidden photon or dark photon connects to entire dark standard model. And that dark fermion could carry millicharge. And in this case, it could be TeV scale. That's not longer ultralight, but you could still actually look for it with quantum sensors. That's why I kind of mentioned, but not to confuse it with the whole ultralight effort. So it's a very different scenario. Okay, there was another question, yes?
The dark matter dark photon would be massive, right?
Yes. Well, it's massive, but it's ultralight massive. It has mass, but it's so this version is ultralight. It can be like 10 to the minus 6 eV. So not to be confused with the mediators, which could be like MeV scale. That's a different thing. So I mean, it's still dark photon. So dark photon, there's a lot of things which can be dark photon, but dark photon could just be ultralight, and just you look for it pretty much with the same devices you look for axion, because it also induces electromagnetic fields in a vacuum. That's what it does.
How do you give mass to the dark photon?
What?
How do you give mass to the dark photon?
I have no idea how to generate mass for dark photon. Anyone has an answer for here? In fact, yes? Right. So, but as I said, we haven't discussed essentially what generates the masses. We know how you can generate dark photons, so you can produce dark photon in the same way through vacuum misalignment, for example. But what mechanism generates mass is a whole different question.
It's any spontaneous symmetry breaking.
Yeah.
Either via Higgs or
Right.
condensation of the dark.
So you have spontaneous symmetry breaking, and you have explicit symmetry breaking when actually the field starts oscillating and acquires mass. There is a little bit of distinction to what I specifically showed how the vacuum misalignment work, but there is a case of photon, vector photon for the misalignment mechanism is considered in, I think, chapter 2 or 3 in the book. Okay?
Can I ask something?
Of course.
To account for the mixing, so for the origin of the kinetic mixing, does one assume the existence of very heavy decoupled fermions which carry both charges, for example?
Yes, I haven't mentioned that, right. So one of the issues then that technically immediately charged particles can be either both positively or negatively charged. Generally, we've been looking for the positively charged because negatively charged can actually bind to that can bind to nuclei, which is a totally different effect. We generally assume there is some sort of symmetry violation which does not make them all annihilate away. So you have visibly charged.
When I said both charges, I meant both the electromagnetic and the dark electromagnetic in a very heavy decoupled
No, I think this is completely decoupled. So in the case of the kinetic mixing, your dark matter only talks to the standard model through the kinetic mixing portal. It doesn't talk directly at all to this. I mean, you could make other versions of mixing. But this is why people introduce concept of portal. Essentially, we are talking about a hidden sector dark matter, which is so weakly interacting, it's only connected through very specific essentially portal. Either you can do through the charge current, which neutrino actually is a good charge current, Higgs, or the dark photons. But there is no other interactions which involve between except gravitational.
The UV origin of epsilon, basically. So if there is some loop of fermions, very heavy fermions that makes
That I don't know.
photon, or you just put it there because it can be, does it get renormalized? Does it run?
Well, there is a different versions of dark photons. So the kinetic mixing, it's not the only way you can generate it. So as I said, I have not looked at the full scale theory here. But in principle, you could actually have this minimally coupled dark photon. The limits are different just because the effects are different. So, but the outcome is the same. You're coupling the two sectors in this case. So this new, I will link to the New Horizons paper. It's actually have references which probably does have answer to this question. My research familiarity is mostly with scalars and some with axions. So, okay. So how do you look for this? So pretty much you are producing the electromagnetic fields in vacuum. So many same type of experiments in this case. So the IDMX, or also experiment called dark DM radio. So DM radio is specifically actually geared toward looking for the kinetically mixed photons. And those, again, you're just producing electromagnetic fields in this case. And the other vector coupling, so technically, you can make more complicated ones. And that actually will produce dipole interaction. what it will do, it will produce a spin torque, and again, you look through the spin precessions. So this is, I think, it, right? Only 4 for the vector. And you can also, in the same way, couple an axial vector. So axial vector only allowed in the lowest dimension only 1 coupling. Because here we need to be able to produce extra gamma 5. So this is the simplest coupling which you can write for this. So you coupling to fermion, and again, that will produce a spin torque. And this kind of all of that generates a list which I showed you yesterday. So remember the effects. It can modulate the value of fundamental constants. It causes precessions of spins, and that's what spin torque is. And when I say precession of spins, all the spins, electronic spins, nuclear spins, whichever is easier to look for. It induces electromagnetic fields, and in some cases, it directly can actually produce single photons. And also, when it modulates the value of fundamental constants, there are several effects. And the one effect is that you modify the energy levels. The second effect, there is effect to the local gravitational field. And the third effect, that it actually modifies the lengths of the solid bodies. So if you have a cavity, which is like silicon, what it will actually do, it will make the length of the cavity oscillate. That's actually why some of the newer cavities are actually sensitive to this as well. The reason why this is happening is because the length of the cavity, especially when it's literally has some lattice structure, the lattice sites are actually connected through the Bohr radius. So if alpha oscillates, Bohr radius oscillates, therefore you actually will have oscillations inside the cavity. However, for the oscillation to happen in a cavity, you have to be able to not exceed the speed of sound, because otherwise it just cannot spread through the cavity fast enough. So there are very interesting comparisons of what exactly happens when you compare a clock to a cavity, when the cavity cannot respond because you're exceeding the speed of sound in the cavity. It's very interesting because then you're actually oscillating around the average value of the Rydberg constant. And there is a bit controversial what exactly happens in this case. So as you see, the spin precession, the energy levels, and the length of the solid body's gravitational field, that means you cover magnetometers, atom interferometers, atomic clocks, and also gravitation wave interferometers, matter wave interferometers is the atomic ones, and also pretty much any spectroscopy experiments is sensitive to this as well. So, and that's also trapped ions can actually feel extremely small electric fields, and that makes them sensitive to dark photons, and so in some of the other more exotic qubit systems. So as you see, pretty much the entire range of quantum sensors is sensitive to one or more of these effects. Questions? So I wanted to show the whole range of different sensitivities to this effect. So let me actually connect, show you some references for this and show the slides, and then we actually talk about specific experiments. So think about questions meanwhile. So you see, so much things to do. You just essentially, made life very busy for like 100 of quantum information groups and various other precision detectors who are actually surprisingly happy to be looking for dark matter. I literally, when I usually visit a lot of my colleagues, and I've literally been asked, okay, here's my detector, here's what we can do, here's my 100,000 of trapped ions. Like, what dark matter can I detect? I'm surprised actually how interested community in the things which is completely remote from what those detectors were originally built for. And now we're also getting to the point that we would like to actually find particular systems when those effects are all enhanced. Because not in all atoms, not in all systems, those effects are the same. Okay, so let me... And a lot of those are new. Oh, go ahead.
Regarding aging lines, because there is like, for example, a new
XMU would break explicitly the invariant of the Lagrangian.
Why?
How does XMU transforms under a gauge transformation?
Well, that is a good question. So, in this case. So, as I said, that's been, we wrote all of these things down. So generally people look at this, things like this. So, but in principle, this is not an impossible coupling as well. So generally, I guess a general rule for all of those, you're transforming them exactly the same way you transform standard model fields. So, I mean, you could problem them as terms, just this is why, I mean, this is, of course, much more natural type of coupling. But I think the general rule, the way we write it, we're essentially writing them in a way that they're transforming in a similar way. So. So I should connect to Zoom? Other questions? Yes?
Sorry if I just missed this, but how would you differentiate like a dark photon and an axion signal in something like a
In this case, response of the, so essentially, what people do right now is that you do not see anything, and then you interpret it in terms of different parameter spaces as of now. When you actually see the signal, that's a good question of how you decouple it. But I think this is easy to decouple because there are different types of experiments which you can do. And some of them have sense to dark photons and some are not. But for, I said the same thing with clocks. You see any signal, you'll eventually sort out what that was. So for now, we are talking about restricting just different parameter spaces with the same type, sort of the same type of measurement.
Recording in progress.
Okay, and share screen. Okay. Oh, Roberto, do we need to press any button here? Yeah, oh, maybe I'm not sure. Just a moment. Yeah, I'm sorry, I'm not sharing. Yeah, you're right. I'm sorry, my fault. Yeah. Okay. So as I said, this summarizes our list of all those different fields. So now you see where actually those things come from. We actually specifically look in some more details. I'll write on the board how that is derived. And now the other question, when you actually talk about detection, one has to distinguish what exactly are we detecting here. So for the most of the cases, we assume that the sun is moving with Earth around the galactic center, and for all purposes, there is essentially dark wind, so we're looking at halo. As I said, this is not necessarily the only picture. especially with ultralights, there could be clumps in the solar system around the sun or the Earth, or there could be actually clumps in terms of axion stars or cue balls. Your dark matter can actually be connected collected in some sort of clumps. All of that will actually modify the detection. So in this point, for the most cases, if you're not actually saying that you're having anything beyond the standard HLL model, in all of those searches, you do assume your particle is 100% dark matter. And then the density is 0.4 GeV per centimeter cube. So this is true for all kind of particle direct searches. This is not the case for the fifth force searches. For the fifth force searches, you're not assuming any density. Those are density independent. They're not dependent on the case of how much dark matter you have, because that actually induces interactions, and that's what you're looking for. Okay. So now, if you're interested more on the scalar and vector dark matter, so anything in this and anything for the scalar, there is 700 references in that paper. It's about 60 pages paper. This is also was produced as a part of a SNOMAS. I will actually link that to the website. And also, in this case, there is an axion dark matter paper. So if you want to know anything about this, this is about 150 pages total. If you want to know the short summary, you can just read executive summary on both of the papers. Also, that actually went to the Cosmic Frontiers SNOMAS report. And now, this is a dilatonic coupling. We actually go over this. So what I wanted to show is this. So here are all the different experiments which can look for either scalars, all the vectors. Just because the axions generally been reviewed many times, we thought we'll put it all together. So this is various magnetometers, various astrophysical probes goes to 10⁻18, the optical gravitation wave detector. This is actually a haloscope, meaning that you can actually search for those dark photons, kinetic mixing dark photons, with the detectors which are geared toward axions. Here is atom interferometers. Actually, atom interferometers are sensitive to both gauge coupling of vector bosons and to the scalars. Clocks are sensitive only, I would say, only to scalars for now. And then there's a cavities or cavity to transitions. And there are various, when we say mechanical resonators, this is a lot of them is optomechanical, this levitated nanospheres, for example. And this is a classical equivalence principle test. We actually, they're sensitive for that entire range, but essentially there's a flat limit for all of those. And it's a limit when you're kind of in between the ultralight dark matter and light dark matter. You actually look at the dark matter absorption. So in this case, this is not entirely kind of wave-like. You do absorb dark matter. So as you see, there is this fantastically large effort in this direction. And those are already experiments which have been ongoing at this point. So is there any questions? Okay. So generally, I will more talk about clocks, but before I do that, I wanted to kind of make a pictures of what we mean by different quantum sensors. So we talk about clocks, which measures the frequency. The magnetometers measure magnetic field. Atom interferometers actually measure phase. And trapped ions could actually measure electric field. And nanoparticles actually can measure forces, like a physical force in this case. And all of those. And that's why between this, you pretty much cover all of the effects which are written in here. Okay, in the remaining 5 minutes, I want to show you actually why, if you have a dilatonic coupling, that actually causes a change in fundamental constants. It's a relatively straightforward derivation, even though it's more straightforward for the masses in comparison to the alpha. And just so you have a kind of a visual, here essentially what we would like to get, it's this. So let's write, I will use slightly different designations just to make it more standard. So all we are doing, we're just coupling our scalar particle to the standard model Lagrangian. And in this case, what it means is that we actually have extra term in addition to the normal standard model Lagrangian. And I'm going to write it in a more proper units in this case. So this is a coupling constants to electromagnetic field. And now the units are inverse energy in this right now. And then you actually have a couplings to various fermions. I'm going to properly actually write the C squared. And all of that gets multiplied by the square root of hc, just to make the dimensions right, and phi. So and remember the phi oscillates. So this is the extra term which you get, and plus you actually have various gluonic terms, and there is some additional terms contributing to the this term from the to the quarks from the gluons as well. I'm going to these are written over here, so I'm just going to omit them and just deal with the first part because there is really no difference for the rest of them. Question?
So this is a non-renormalizable program.
Why?
X is the axiom.
No. This is not x. This is just multiplying.
Oh, sorry.
No, this is just multiplying by phi, by a scalar.
But phi dimension 1, mass dimension 1, right?
I think so.
Everything else is mass dimension 4. So.
So my understanding that in this case you can actually make a for the scalars, as long as you put, so for the scalars itself, you actually can end up with a fully renormalizable theory, but I'll have to say that this is beyond my expertise. So, but there is a number of references in the scalar paper which actually looks at that. So, but let me think about. So I don't think so because we are. Let me get back to you on this. So let me ask one of my particle physics experts. Okay.
It is not renormalizable, but there is no problem. You can have. Yes.
Okay. But let me ask this for the, as I said, sometimes I ask my different particle physics colleagues because sometimes I get different answers. So sometimes it's quite interesting. Okay. And now like with this term, it's kind of straightforward. Okay. So with this term, it's actually straightforward to see what happens. Because now this is your additional term. And when you actually have your additional term, let's compare what actually your standard model Lagrangian is. So your standard model Lagrangian is gamma mu, phi minus c squared, phi minus a charge, gamma mu, a mu, minus 1/2 F mu. Now, this is a standard model part, and comparing those two terms, it's kind of obvious what actually happens to the mass, right? Because you can just now put those two terms together, let's say for the electrons, and you can see that the mass just gets adjusted by additional oscillating term. So when you put those two Lagrangians together, the mass now goes to the mass 0, which mass 0 is what it would have been without actually any of those dark matter. And so this is our gamma F, let's say electron, and Hc phi. Okay. So this is why the mass, all the masses become oscillating, because you just added the term which oscillates. And this is kind of the critical point here. So all the mass terms are automatically oscillatory because you just added the terms of our Lagrangians which oscillate. Effectively, that corrects the mass. So experimentally now mass is different. So any questions on this one?
On the detector, what we see when there is a oscillating mass, mass is changing with time.
Okay, it's a very interesting question. So how do you separate changes in units from changes in quantities? So what you actually express dimensionless units first. So what we are looking, not a variation of mass, but variation of mass ratios. A natural one is electron to proton mass ratio, or the quark masses to the QCD scale. So experimentally what it looks, it's that energy levels become, or the frequency ratios become oscillatory. And experimentally, it's essentially you're just extracting the oscillation signal on top of the no change. Okay. By the way, just to say, oscillations, it's the simplest thing which dark matter can do to fundamental constants. There are way more other interesting cases. If you have domain wall passing through, you're going to actually have a transient change in fundamental constants while it's passing through. Having cold domain walls contradicts a lot of things, however. So there are various cuboles and monopoles. There's also possible to have transient signals from these exploding stars, action stars. So there are various other signals besides oscillations. It just oscillations is always on, because if you have dark matter here. Okay, now it's slightly more involved. What do you actually do to this? So let's first actually compare those two terms. Question? No? Okay. So let's compare those two terms. So let's rescale the Faraday tensor. So let's separate this one. So we have 1 minus gamma alpha square root h bar c phi. And in this case, let's just say that now, let's rescale it to the f mu prime 1 minus, and this is minus 1/2. Okay, all we are going to do is redefine it. And if we rescale it, we also have to rescale the a mu as well. So the a mu then gets rescaled in the same fashion. There is a little bit of supposition here. The supposition here that the field is not varying much over your detector. This is actually for the masses we are looking at those detectors, this is actually true. And now, since you're actually redefining this, what you are doing, you are redefining the charge term. Oh, actually, I can, let's do this. So let's look at our charge term with a vector potential. So what you now have, it's this. This gets redefined. A prime mu and the square root minus gamma alpha square root of h bar c hc phi. Okay, and what are we going to do with this? Well, we remember that alpha, it's your q squared divided by the hc. So this is our fine structure constant, and this would be electron elementary charge. Therefore, the alpha is redefined as alpha 0 divided by the 1 minus gamma alpha h bar c phi. And we are going to just say that in this case, this is much less than 1. So this is approximately alpha 0 plus gamma alpha. So as you see now, alpha is oscillating too, because you just couple it to oscillating field. Questions?
Let me just check if I got this right. Like, we have this first Lagrangian that has the G-level multiply and everything, plus the Lagrangian
Yes.
without it.
Yes, there is a standard model Lagrangian, plus now a new part of the Lagrangian, which is just literally multiplied by your oscillating field. So what we're doing right now, we are coupling two together, And essentially, every term which we have in a normal Lagrangian, we now have additional term from that Lagrangian. When you put them together, you can see that all masses become oscillating, and all the coupling constants. It's actually a strong coupling constant would actually also oscillate as well. So yes, that's exactly what we're doing.
It would be a small summing that was oscillating just a little bit.
Yes, it's a very small. Yes, absolutely. So the coupling here is very small. So all of that is essentially kind of the hidden dark sector couples. I mean, if those things couple strongly to the standard model, we should have seen them by now. So the fact that actually we have not seen them in any of those experiments, the couplings are small, absolutely. And that's why we kind of don't see them in normal life, but this is why it's so hard to detect dark matter. The interactions are feeble. Other questions? Okay, so the next time we will actually first have some introduction into the atomic clocks, and then I'll actually show you different constraints from all those different experiments, and also we then talk a little bit about the axion detection. And that time actually some of the fraction would be in PowerPoint because I have to show you some of the experiments, and we also talk about very interesting questions, the challenges for particle physics when we would like to actually detect those things in space, because there could be completely different signatures. And I'll show you some of the few of the ideas for the detection in space. And then on Friday, and maybe if you have time, we'll talk about ADMs tomorrow. If not, that we'll actually have time on Friday. And tomorrow, at the afternoon discussion section for 30, that's where you start presenting your committee results. So you can either send it to me, make some sort of PowerPoint or PDF presentation, and or you can actually just use your own laptop and connect it, whichever works. But it's 5 minutes, so it's easy if you just send it to me and just write your names as a kind of committee members, and that's our proposal, what we decide to build, and which problems we would like to solve. If we presumably we will, an hour will be too little, so we'll use some of the Friday lecture. If you need a Friday discussion section, then that can be done as well. So, okay. There is not schedule. So there is not schedule right now, but Diego is coming, so we'll have to discuss. So, yeah, as I said, I'm here. Okay.
So the discussion are say, flexible, okay? So first of all, I remind you there is one today. So let's start with the close horizon. After Luca's lecture, there's going to be discussion with him. And then we are free to extend it, including, even the length is not fixed. There is no welcome drink coming after. So tomorrow we can discuss if we want to have it.
Tomorrow they will have the presentations.
Yes, if we want to extend the time or change a little bit the time.
We will see. I think the 4:30 is a good start. I mean, people need a break. So,
yeah, I mean.
But if we're probably not going to be done with 10 groups, so we can actually start Friday lecture with the remaining presentations.
Okay, it's up to you if you want to have them all together when we can. So timetable is flexible. You are all coming here, so you will be. It will be announced if there is any change. And I remind you to sign the present sheet. Okay, only one person is missing, but. So I'll see you at 2 p.m.